Welcome to this lecture of differential geometry. This lecture will be designed in the context of entrance test only. So this lecture will be specifically helpful for preparing students for the entrance tests in differential geometry. So our focus will not be on explaining the groups or delving deeply into the formal definitions or the theorems, but instead we will concentrate on understanding how effectively we can apply the results and concepts to solve the problems. So we start with here in this lecture or in the following lectures, we will mainly study about the space curves or the curves on plane and the surfaces. So here we have the differential geometry that we shall shortly write as DG, and we will be taking just two topics mainly. So it is one of the topics is curves and the second is surfaces. Now here we will study these curves in the context of Rn, where n is greater than or equal to 2, and we will study surfaces in the context of Rn, where n is greater than or equal to 3. Now here, before going further, we shall here mention that if n is equal to 2, in the context of Rn, or in the case of curves for Rn, if n is equal to 2, then we will be dealing with the curves that are drawn on the plane. And if n is greater than 2, we may call them as the curves which are in space, or the space curves. And similarly, we will do the surface in Rn where n is greater than or equal to 3. Now here we have some standard notations. We will have a set U that we shall always treat as a subset of Rn, and a set V which we shall treat as a subset of Rm. And then we define a function, or we may call it a map, f from U into V. So we will always have this function f or a map f from U into V. Now let's take up our first definition, that is a smooth curve. A map f from U into V is smooth if f is infinitely differentiable. That is all partial derivatives of f, which we shall denote by del and f, and we can define them in this way: del alpha 1 plus alpha 2 plus so on plus alpha n of f with respect to some n variables, del x1, and this is the derivative of order alpha 1. Similarly, with respect to x2, the derivative of order alpha 2, and so on with respect to xn, the derivative of order alpha n, where we will take this alpha as alpha 1, alpha 2, alpha n. And in fact, this will be an ordered n tuple in nn, the Cartesian product of n with itself n number of times. Now actually here we have, this is alpha. So alpha derivative of f with respect to these n variables x1, x2, xn, this must exist and continuous. Then we will call the curve as a smooth curve, and now we have one notation, and we will denote the set of all smooth curves always by C infinity, and if they are from U into V, then we will write C infinity U into V. So this is the set of all smooth maps from U to V, and U is a subset of Rn, V is a subset of Rm. Now let's take up one more definition that we must be knowing, so that is diffeomorphism. These are some nice terms that we might be using in our lecture, or maybe sometimes questions are asked where they use the term diffeomorphism or likewise. Now we call a map f from U into V is a diffeomorphism if f is bijective with both f and f inverse being smooth. So a diffeomorphism is a bijection between a subset of Rn to a subset of Rm, which is a smooth map, as well as its inverse is a smooth map. Now let's take up one more definition when we call a map as regular. So this is a map f from U into V is regular at a point say P of like Rn if the derivative of f is not equal to 0. If this df by d, we can say the variable u is not equal to 0 at P. Now let's take up the notation for a curve, and we will begin with a curve which is a plane curve, or it may be a space curve. Now curve will always be denoted with this notation r equal to r of t. This can be represented either in the coordinate form or in the Cartesian form. We can write it in this way: x of t, y of t, z of t, or this can also be expressed as xti plus y of t j plus z of t k. So this is actually a space curve. Now here to mention that if we have a plane curve will be defined with only two coordinates, x of t, y of t. Then z coordinate will not be there, and space curve in general will have three coordinates, and this can be expressed as x, y, z, where each x, y, z is a function of t. Or we can also express it in the form of x of xi plus yj plus zk. In fact, we have this is an equivalent form to xi plus yj plus zk. So these will be some notations for representing a curve, and similarly we will represent a surface. Now surfaces will usually be represented in this way. The first coordinate will be x of uv, second coordinate y of uv, and third coordinate z of uv, which will be a surface in R3. Now here the difference between a space curve and the surface in terms of notation is that a space curve will be represented with three coordinates, but each coordinate is a function of a single variable t. But however, surface, when represented as a surface in R3, when represented in this coordinate system, then each coordinate will be a function of two variables. So now we can proceed with our first definition, which is the arc. Now how do we define the arc length? The arc length of a space curve is the total distance along the curve between two points. Like suppose if we have, this is our curve, and we have a point A here, and we have a point B here. Then the length of this curve from A to B, which is in fact not a straight line distance, but the distance of this distance from A to B along this curve will be called the arc length of this curve from A to B. Now here we provide the formula for evaluating this arc length of a space curve, or we can use the alike formula for the curve in plane as well. So let r of t is equal to x of t, y of t, z of t. Suppose we have, this is our space curve, and if the curve happens to be a plane curve, then we will not have the z coordinate. Then arc length is arc length from A to some point u is given by, which we shall denote by s, or which can be now a function of s of u. So this is the integral from A to u, the norm of r dot of t dt. Now we know that the norm of r dot can be expressed in this form. So this is the integral from A to u, square root of x dot square plus y dot square plus z dot square dt, where this dot will denote the derivative with respect to t. So this r dot means dr by dt. So this dr by dt can be expressed as dx by dt, dy by dt, and similarly dz by dt. So that's how we evaluate the arc length of a curve. Now we will take an example to apply this formula for evaluating the arc length of a curve, and in fact we will take one nice example of a curve that we call the circular helix. Now it will be left as an exercise to know what is the figure of the circular helix and what is the definition of a circular helix. Here we will not take up the definition, but we will just take up the coordinates, or we will just take up the parametric representations. Here we will just take up the parametric representation of the circular helix. A circular helix is represented by r of t with coordinates a cos t, a sin t, bt. And this will be the circular helix which wraps around the z-axis. So this wraps around z-axis, or we can call z-axis will be the axis of this circular helix. Similarly, if we write the circular helix which wraps around the x-axis, so we have to write it like this: bt, then a cos t, a sin t. Then this will have its axis as the x-axis. So this kind of a helix will wraps around x-axis. Now we can similarly understand how to write down the equation of a helix, or a parametric equation of a helix which wraps around the y-axis. Now we can also write down the elliptic. So this is the definition of a circular helix, or the parametric representation of a circular helix. We can also have some other helices, like we will have the elliptic helix. Elliptic helix will have its parametric representation as r of t is equal to a cos t, then b sin t, then ct. Now, as we actually, how do we understand whether how this is a circular helix and the second one is an elliptic helix? If we look at these two first coordinates, a cos t and a sin t, this is the parametric representation of a circle. X square plus y square is equal to a square. So this circle makes this helix as a circular helix. And similarly, these two, a cos t and b sin t, they are the parametric representations of a ellipse, which is x square by a plus y square by b equal to 1. Now, in fact, if a is equal to b, then this will also give us the circular helix. Similarly, we can define the spherical helix, and we can define the helix on a cone. Spherical helix will be left as an exercise, but here we will mention the parametric representation of a helix on cone. It is having the representation at cos t, at sin t, and bt. Now again, here the first two coordinates, these actually represent the parametric equation of a parametric representation of a cone. Now, in order to write down the parametric representation of a circular helix, we need to first write down the first two coordinates, which must represent a sphere. Then the third coordinate will be taken as bt to write down the equation of a helix drawn on a sphere. Now let's take our first exercise. Find the arc length of the circular helix with the parametric representation r of t is equal to a cos t, a sin t, bt from the point a0, 0 to a0, 2 pi b. Solution. Now, as we know that this helix is a helix which is wrapped around the z-axis, so we will have this coordinate. X-axis coordinates are a to a, which is equal, and y-axis coordinates are again equal, but the z coordinate is from 0 to 2 pi b. So first of all, we need to find the limits for the integration. Use it in the formula for finding the arc length. The limits of t are from this bt equal to 0 to bt equal to 2 pi b. Because the helix is wrapped around the z-axis, so the z coordinate varies from 0 to 2 pi b, which gives t is equal to 0 to t is equal to 2 pi. Now, as we know, from 0 to 2 pi we have one complete rotation of a circle. So this question can also be asked in this way, to find the arc length of one complete turn of a helix. So now, keeping this thing in mind, so this interval gives the length of one complete turn. In fact, the circular helix means a helix which is drawn on the right circular cylinder. In fact, in order to understand this more nicely, we can draw it like this here. So let's keep this is the right circular cylinder. So this circle will have the equation x square plus y square is equal to a square, and this vertical axis is the z-axis. So this is the z-axis. Now the circular helix is actually a spring-shaped figure that wraps around this cylinder. So like suppose it starts from here, then it rolls like this. So that is the shape of a circular helix. Or let us draw it like this. So circular helix is like this. It is a spring-shaped figure wrapped around the right circular cylinder. Similarly, if we have the spring-shaped figure wrapped around an ellipse, we can call that an elliptic helix. Similarly, the spring-shaped figure wrapped around a sphere, we can call that spherical helix. And similarly, if we have like a cone like this, then we will have the spring-shaped figure wrapped around this cone. So it will have this kind of a structure, which will be called a ellipse helix on a cone. Now we need to find the length of the circular helix from 0 to 2 pi, which is in fact one complete turn of a helix. So therefore, the arc length is from 0 to 2 pi is integral, or we can call that S is equal to integral from a to 0 to 2 pi, the norm of or dot of t dt, which we can also write as integral 0 to 2 pi, then square root of x dot square plus y dot square plus z dot square dt. Now we need to evaluate this r dot norm, or we need to evaluate the square root of x square plus y square plus z square. So now we are given that given r of t is equal to x of t, y of t, z of t, which has the values a cos t, a sin t, and bt. So this gives r dot t, which is the derivative x dot, y dot, z dot, which we can now write as minus a sin t, here a cos t, and here just b. Hence, this norm of r dot of t, which is defined as square root of x dot square plus y dot square plus z dot square. This is equal to square root of, now a square sin square t plus a square cos square t, that is just equal to a square, then plus z dot square, that is equal to b square. So therefore S is equal to integral from 0 to 2 pi square root of a square plus b square with respect to t. Now evaluating this integral, we will get 2 pi square root of a square plus b square. So this is the length of one complete rotation of a helix, from one complete rotation of a helix with in its general form wrapped around the z-axis. The helix has also representation of a helix. We can write down the helix in this way also. R of t is equal to a into 1 minus t square divided by 1 plus t square. The second coordinate is a into 2 at divided by 1 plus t square, and the third coordinate is 2b tan inverse t. So this representation is also a helix, and in fact we can also express our helix as the intersection of two surfaces. Now the circular helix as intersection of two surfaces. Here we have the two surfaces. The first one is like f of xyz, which is given by the equation x square plus y square is equal to a square, and the second is g of x y z, which is defined as like x is equal to a cos z by b. Now this will also represent a helix as the intersection of these two surfaces. So first surface is the circle with radius a, and second surface is this thing. Now in fact, how do we understand this is a helix? If we put z is equal to like bt, then we get x is equal to a cos t. So which satisfies here, and here we have x is equal to a cos t, y is equal to a sin t, and z is equal to bt, which is actually the previous parametric representation of a helix. Now let us define the tangent line. Let our curve be given as, let r is equal to r of t, having the coordinates x of t, y of t, z of t. Then tangent at any point P with coordinates x naught, y naught, z naught is given by the equation r minus r is equal to lambda r dash. Now we have used new notation r dash for denoting a derivative actually. So first of all, if we have this r dot, or if we have this r as xi yj plus zk, then in differential geometry most of the times this r dot is the derivative. So this is dr by dt. And if we write the same curve as x, y, z in the Cartesian form or in this coordinate form, then we denote r dash by dr by dt. So this is just a notation, so r dot and r dash is one and the same thing. Now here we can write the equation of a tangent in this way, r minus r equal to lambda r dash, where this r is the original curve x, y, z, and r dash is its derivative, and this r, capital R, denotes some new variables for writing down the equation of a tangent. this can be written in the Cartesian form as x minus x naught divided by x dot is equal to y minus y naught divided by y dot. This is equal to z minus z naught divided by z dot. And in fact we also need to evaluate this x dot at x equal to x naught. We need to evaluate y at y equal to y naught and z at z is equal to z naught. So this is how we can write down the equation of a tangent to a curve. But now we can have the curve given as the intersection of two surfaces also. So that will be our case number 3rd. If the given curve is given as the intersection of two surfaces, say the first surface is f of xyz equal to 0 and g of xyz equal to 0, then equation of tangent at P with coordinates x naught, y naught, z naught is given in this way. It is given in the parametric form with x of t is equal to x naught plus say at, y of t is equal to y naught plus bt, z of t is equal to z naught plus ct, where we have these new variables here a, b and c, where this a, b, c, they are actually the three coordinates of del f cross del g at the point P. So this actually represents the gradient of these two vectors. So this is cross product of gradients. This is how do we write down the equation of tangent to a curve when it is given as the intersection of two surfaces. The three coordinates of that equation of tangent are x of t equal to x naught plus at, y naught plus bt, z naught plus ct, where these a, b and c, they are the three coordinates of del f cross del g evaluated at P. Now we are ready to take an example to understand how do we find this equation of tangent. So our first exercise will be find the equation of tangent to a circular helix given as, now we will take it the both representations of the circular helix given as r of t is equal to a cos t, a sin t, bt, which is in fact a circular helix wrapped around z axis, and we will take it as given as intersection of two surfaces given as intersection of x square plus y square equal to a square, and say x is equal to a cos z by b. Or we may take another question also, find the equation of tangent line to a curve given as intersection of two surfaces, say f is equal to x square plus y square plus z square minus 1 and g is equal to z minus y at P with coordinates 1, 2, 2. Now this point 1, 2, 2 lies on sphere as well as on this plane z minus y equal to 0, or x square plus y square plus z square minus 9 equal to 0. Now let's take the solution. Exercise number 1 given r of t is equal to a cos t, a sin t, bt. Then this r dot u is equal to, now let's take the derivative at u. So first the derivative is minus a sin t, but at u it is equal to a sin u, and similarly here a cos t at u we will get a cos u, and this is b, and similarly r of u, this is equal to a cos u, a sin u, bu. Therefore we can immediately write down the equation of the tangent. The equation of tangent is x minus x naught divided by x dot equal to y minus y naught divided by y dot is equal to z minus z naught divided by z dot, and we can write this is equal to lambda r. Now this x minus x naught is equal to a cos u divided by x dot, this is equal to minus a sine u, this is equal to y minus y naught, that is equal to a sine u, divided by y dot, it is equal to a cos u, and z minus z naught is bu, divided by its derivative, that is equal to b, this is equal to lambda. So therefore this is the equation of tangent to a right circular helix at the point a cos u, a sine u, bu. Now let's evaluate the equation of tangent to a curve when it is given as the intersection of two surfaces. For that we will do the second exercise and leave the second part for the right circular helix as an exercise. So this left as an exercise, and we will do this exercise f equal to this and g equal to this, and write down the equation of tangent at 1, 2, 2. So first we are given that f of x by z is equal to x square plus y square plus z square minus 9. We can see this is equal to 0, and g of x y z is equal to z minus y is equal to 0. Now in order to write down the equation of tangent, we have certain steps to follow. The first step will be compute this del f at p and del g at p. Now once that is done, second we will compute their cross product. Compute this del f at p cross del g at p, and we will get this as a vector in R3. We will denote that vector by ABC. Then third is equation of tangent. Equation of tangent is x naught plus at, y naught plus bt, z naught plus ct. So this is in these three steps we will evaluate the equation of tangent. So now let's follow our first step. So here we have del f, which is equal to, with respect to x. Okay, so let's first define what we mean by this del f. It is fx, fy, fz. This is equal to 2x, 2y, 2z. Then del f at the point p is equal to del f at the point 1, 2, 2. So this is equal to 1, 4, 4. And second is del g, which is equal to gx, gy, gz. This is equal to 0, 1, 0, minus 1, 1. And then del g at p. So this is obviously equal to minus and 0 minus 1 plus 1. Now let's take their Cartesian product. So next, this del f of p cross del g of p. This is equal to I, j, k. Then here first vector 1, 4, 4. Second vector 0 minus 1 plus 1. Now evaluating this cross product, we get I times 4 plus 4 minus j times 1 minus 0 plus k times minus 1 minus 0. So this is equal to 8i minus j minus k. And we can also write it in the coordinate form like 8 minus 1 minus 1. Hence the equation of tangent is x naught plus at, y naught plus bt, z naught plus ct. Now x naught is equal to 1 and a is equal to 8. So this is equal to 1 plus 8t. Y naught is 2, b is equal to minus 1, so it is 2 minus t, and again here 2 minus t. So this is the required equation of tangent. Now let's take up another topic which we call the contact of order n between a surface and a curve. So this is contact of nth order between a curve and a surface. This is defined as, so it has a definition like this. A curve gamma of t has a contact of order n with a surface denoted by s, defined as f of x, y, z equal to 0 at a point p, which is defined as gamma of t0. So this is a point lying on the curve if the function f of gamma of t vanishes up to order n. Now what we mean by a curve vanishes up to order n at the point t equal to t naught, That is, first we have this f of gamma of t naught. This is equal to 0. F dash of gamma of t naught. This is equal to 0, and so on. The same thing happens up to the nth order derivative fn of gamma of t naught. This is also equal to 0, and finally the n plus 1, the derivative fn plus 1 of gamma of t naught. This is not equal to 0. So this is what we mean by saying a curve gamma of t has a contact of order n with a surface. This actually refers to how closely the curve coincides with the surface near that point. So in other words, we can say that a contact of nth order for a curve means that the curve lies on the surface to order n but departs from it at order n plus 1. Now we will here take up some basic intuitions like what we mean by a curve has a contact of 0th order or the first order or the second order. Orders like 0th order means the curve passes through the surface. Second, first order, that means the contact of first order. First order means the curve is tangent to the surface. That means there lies a straight line that is tangent to both the curve as well as to the surface at some point. So this curve and the surface touch each other at just one point. Now second order contact means, the curve has the same curvature, direction. So we are here given a curve and a surface. So the second order contact of the second order for a curve and a surface here means that the curve and the surface have the same curvature direction. So similarly, this higher order contact means the curve increasingly resembles a surface, or we can say a surface curve near the point. Now here we will try to find out how do we find the condition that a given curve and a surface have a contact of order n. So here we have this to find a condition that a curve and a surface have an nth order contact at a point P, say with coordinates x naught, y naught, z naught. This is taken as, let the curve R with suppose coordinates x of t, y of t, z of t. So this is now in fact a space curve, and let the surface be, and let f of x, y, z equal to 0 be the surface. And then first step is eliminate x, y, z between r of t and f of x, y, z equal to 0. That means for x in the surface we have to substitute x of t, and for y we will substitute y of t, and for z we will substitute z of t. That will help us eliminating the variables x, y, z from the surface and replacing them with the variables t. Then second is find the common solution of this f dash of t equal to 0, f double dash of t is equal to 0, so on. Now fn minus 1 of t is equal to 0. So we will from the first up to the n minus first order derivative, we will find the common solution of these n minus 1 equations, and their common solution will be the condition that the given curve and the surface have the contact of nth order. Now let's take up an exercise in this direction. This is find the plane that has a contact of order 3 at the origin with the curve or with the surface given by x is equal to t power 4 minus 1, y equal to t cube minus 1, z is equal to t square minus 1. So in the solution, our first step will be to eliminate. First, let's write down the equation of a plane passing through the origin. The equation of plane. So here in fact we don't have this as our, this is the curve. The equation of plane passing through origin is, it can be given like this: ax plus by plus cz is equal to 0. Now our given curve is, so we have, this is our f of x, y, z, and our r of t is equal to t power 4 minus 1, t power 3 minus 1, t square minus 1. So now first we eliminate this xyz from the function f of xyz. So now this f of x of t, y of t, z of t equal to 0 gave us a into t power 4 minus 1 plus b into t cube minus 1 plus c into t square minus 1 is equal to 0. That is a t power 4 plus b t cube plus c t square minus a minus b minus c is equal to 0. Let's call this function as, suppose this capital F of t. So then we have to find the common solution of, so then we shall evaluate f dash of t, which is equal to 4 at cube plus 3 bt square plus 2 ct. F double dash of t, this is equal to 12 at square plus 6 bt plus 2c. Now let's equate both of these equations with 0 and find the values of a, b and c from them. So then solving them, we get a with the cross multiplication rule. It is 6 minus 12, so it is equal to 6 minus 12, which is equal to b divided by 24 minus 8. This is equal to c divided by 24 minus 36. So this gives, now a by, this is equal to minus 6, b divided by 16, and this is c divided by 12, or minus 12, or we can write this as a divided by, now we can write this as a by 3, this is b by minus 8, and c by 6, dividing each by 2. So hence the plan is 3x minus 8y plus 6z is equal to 0. So this is the required plan that has a 3-point contact with this curve given with this parametric equation. Now again, let's come to the theory of tangents. So we have already defined the tangent of a curve. Now we know that vector that is perpendicular to a tangent, that's which are denoted by t. Then we have a vector which is perpendicular to this tangent. Let us denote that by n. Then we will take upon another vector which is perpendicular to both tangent as well as the normal. We will call that as binormal. So it is normal to these two vectors, and we call that as b. So we have these three vectors t, n, and b. Now the unit vectors corresponding to these three are, we can call them as small t, the unit vector which is a tangent, and now the normal n, and the vector b. So they are the unit vectors now in the direction of tangent, normal, as well as binormal. We can treat these three tangents like the three coordinate axis x, y, z. So now assuming that we have, this is our tangent t, we can call that as a unit tangent or the general tangent capital T. Now it has a vector normal to it or perpendicular to it, which we can call by n, and taking this in the direction of y-axis. And then we have binormal, which is perpendicular to both of them. Let's draw it like here, and this is our b. So these three vectors behave in this way, like the three coordinate axes x, y, and z. Now when we have these three vectors behaving in this way, then they will give rise to three planes, one lying between the vectors t and n, so it is a plane here, and similarly a plane between n and b, so we have a plane here, and similarly a plane between b and t. Now these three planes are known as the fundamental planes, which are generated by these three mutually perpendicular vectors. Now the fundamental plane that lies between t and n, that's called the osculating plane. That's called osculating plane. And similarly the plane that lies between n and b, that's called the normal plane. And the plane that lies between b and t, that's called the rectifying plane. We shall shortly denote these three planes by O OP, that means the osculating plane. Then we have NP, that we shall call the normal plane. And we have RP, that we shall call the rectifying plane. Now as we understand it properly, that now this osculating plane, it has this binormal perpendicular to it. And similarly for the normal plane, it has the tangent to a curve perpendicular to it. And similarly for a rectifying plane, it has the normal perpendicular to it. And now here we also have one more definition, a principal normal. Principal normal, what we mean by principal normal? Principal normal is a normal that lies in the oscillating plane. A normal that lies in the oscillating plane is called a principal normal. Now let's again come to these three vectors T, N, B. Since they are mutually perpendicular, we have this T dot N, this is equal to 0, N dot B, this is equal to 0, and B dot T, they are all equal to 0. Now we know that the cross product of two vectors is perpendicular to both of them. Now since they are the unit vectors and we have another property with them, so we have this T cross N. Now since T cross N is perpendicular to both T and B, and that vector we know by definition that is equal to B, a binormal which is perpendicular to both tangent and normal. Similarly this N cross B, now this will be equal to T, and B cross T, this is equal to N. So they also behave in the clockwise in this way. So we have these three vectors. Here we have T, N, B. The cross product of T and N, it is the vector B. So it is in the anti-clockwise direction. Cross product of N cross B, that is equal to T, and B cross T, that is equal to N. And if we take the cross product in the reverse order like N cross T, it will be equal to minus B, and so on. Now based on these definitions that the oscillating plane, normal plane and rectifying plane, they are perpendicular to this B, then T and N respectively, we can accordingly define how do we write down the equations of fundamental planes. Now first of all we take the osculating plane. Now by definition of the osculating plane, it is a plane that is normal to, that is with which B is perpendicular to the oscillating plane. So accordingly we can define the equation of the oscillating plane. It is R minus R. Now since it is B is perpendicular to it, so we can call this is the equation of the oscillating plane. Similarly for the normal plane, we can take R minus R. Now normal plane, T is perpendicular to the normal plane, so we can write down the dot product with R minus R equal to 0. And similarly for the rectifying plane, we can take this R minus R and see that the normal is perpendicular to the rectifying plane. So dot N, this is equal to 0. So this is how we can write down the equations of these three planes. And we also have a very simple representation of an oscillating plane. So that's another result. Equation of oscillating plane can also be expressed in this way. Equation of oscillating plane is also for equation of oscillating plane for R is equal to R of T is given by triple product with R minus R, then R dot R double. This is equal to 0, and this here represents the scalar triple product. Now let's take an exercise. Find the equation of the oscillating plane for a curve R of T that has its three coordinates as T, T square, T cube. So in the solution, we know the equation of oscillating plane is the scalar triple product of R minus R, R dot, R double dot is equal to 0. Now as we know this R is given as T, T square and T cube, we have R dot is equal to 1, 2T, 3T square. The derivative is for all the three coordinates. Now R double dot, the second derivative is 0, 2, 6T. So therefore the scalar triple product is R minus R, R dot, R double dot. This matrix is the determinant of. Now first we will have the coordinates for R minus R, which we can write as x minus x, y minus y, z minus z. And similarly for R dot, the coordinates are 1, 2t, 3t square and now third row is 0 to 60. This is equal to 0, which on evaluation gives the equation 3t square x, sorry, we can write this as x minus t, y minus t, z minus t. Now this gives 3t square x minus 3ty plus z minus t cube is equal to 0. So this is the equation of the oscillating plane to our given curve at any point t. Now if we have some fixed value of t, we can similarly find the equation of a oscillating plane at that point. Now for the practice purpose, let's write down one more question here. Find the equation of the oscillating plane for the curve x equal to t, y equal to 1 plus 1 by t, z equal to 1 by t minus t. And for the verification purpose, I will keep the answer here, that is x minus y plus z plus 1 equal to 0. Now let's mention some properties of these three fundamental planes that we have already. Oscillating plane, we know that it contains the tangent and the principal normal. Tangent and the principal normal. And this oscillating plane can be defined as a best fit plane of the curvature. Similarly, we can define the normal plane as it contains the normal and the binormal. Similarly, we can write down for the rectifying plane, it contains the tangent and binormal. Now we take our another topic, the curvature of a curve. Curvature means the rate at which the curve bends. So we can denote this by, this is the rate of change of the direction of tangent with respect to the arc length, that is called the curvature. Or in simple terms, we can say that it is the rate at which the arc bends at some particular point. This is denoted by kappa, which is defined as the derivative of tangent dt by ds, which we can call as the derivative of tangent, because we know that the derivative represents the rate of change of a curve at a particular point. So now the rate of change of direction of a tangent will be called as the curvature of a curve, and this can also be defined as r double dash. And similarly, we have another term associated with the curve, that is torsion. Curvature and torsion, these are very important terms. This is the rate of change of direction of the binormal. This is the rate of change of direction of binormal of a curve. We call that as a torsion, which is denoted by tau, and defined as the rate of change of direction of the binormal, that is dB by ds, where s is the arc length, and this can also be written as b dash. And now this is defined as r dot, r double dot, r triple dot, scalar product of these three vectors whole divided by this norm of r dot cross r double dot whole square. This can also be treated as a formula for evaluating the torsion. Similarly, as we know that we have three mutually perpendicular vectors, tangent, normal, and the binormal. Now we have curvature, which is the rate of change of direction of a tangent, torsion, rate of change of direction of the binormal. Similarly, we must have the name for rate of change of direction of the normal. That is called the skew curvature. So we have a term skew curvature here, which is the rate of change of direction of normal. Direction of, most of the times it writes principal normal, but principal normal and normal are almost the same. So rate of change of direction of principal normal is called the skew curvature. It is denoted by s, and this is denoted by, defined as square root of kappa square plus tau square. So using the curvature and the torsion, we can easily compute the skew curvature, or we can also express this as s square is equal to kappa square plus tau square. Now let's also write down the formula for evaluating this curvature. The curvature is most of the time is evaluating using the formula like r dot cross r double dot, the modulus of this vector divided by r dot whole cube. Now using these three definitions, let's evaluate the curvature, torsion, and the skew curvature for a given curve. Let's take an exercise. Find these three parameters, curvature, torsion, and skew curvature for the parametric curve r of t is equal to t square t cube. So in the solution, we first evaluate now what we need. For the curvature, we need r dot and r double dot, and for torsion, we need the r triple dot. So let's first evaluate all these three derivatives. So first of all, we have r dot, which is equal to 1, 2t, 3t square. Similarly, r double dot, which is equal to 0 to 6t, and the third derivative is 0, 0, 6. Now again, for curvature, we need the cross product of the first two. Now next is this cross product of r dot cross r double dot, which we can define as here I, j, k. Now in the second, we have 1, 2t, 3t square, and in the last row we have 0, 2t, 6t. Now similarly, for the torsion, we need this r dot, r double dot cross r triple dot. So we need to find the r double dot cross r triple dot. This is equal to I, j, k. Now double dot means 0, 2t, 6t. Now its derivative is, so this is 0, here this is t, and this is 0, 0, 6. Now using these all calculations, we have finally this, so then this curvature, this is equal to modulus of r dot cross r double dot divided by r dot cube, which finally becomes the modulus of, and here actually this is equal to 6t square I minus 6tj plus 2k. Now its modulus will be equal to 36t for 4, then plus 36t square, then plus 4 whole divided by now r dot cube. Now as we know, r dot is equal to 1, 2t, 3t square, so it is whole cube is equal to 1 plus 4t square plus 9t power 4 whole cube. Now by modulus we mean it is the square root of this thing, so it is equal to this 36. We can take 4 common from there, so it is 4 into 9t power 4 plus 9t square plus 1 whole divided by 9t power 4 plus 4t square plus 1 whole power 1 by 2. So that is the curvature of this curve at any point t. Similarly, we can define the torsion. Similarly, for torsion, we have this is scalar product of r dot, r double dot, r triple dot whole divided by r dot cross r double dot whole square. Now this denominator is already calculated in the previous step. We need to evaluate this scalar triple product in the numerator. So product r dot, r double dot, r triple dot. This is a 3 cross 3 determinant with first row as the 3 coordinates of r dot, which are 1, 2t, 3t square. Now its second derivative is 0, 2, 6t, and the third derivative is 0, 0, 6. So this whole determinant is equal to 6. Sorry, this is equal to 12. And similarly, this r dot cross r double dot, this is equal to, or we can say whole square, this is equal to determinant of I, j, k. Now r dot is 1, 2t, 6t, 1, 2t, 3t square, and second is 0, 2, 6t. Now evaluating this determinant, this is equal to 6t square minus 6t. So this modulus of 6t square I minus 6tj plus 2k whole square, and this finally becomes 9, 4 into 9, t power 4 plus 9 t square plus 1 as computed above here in the denominator or in the numerator. So therefore the torsion is, thus torsion is equal to this scalar triple product, that is equal to 12 divided by cross product of 4 square, 4 into 9 t power 4 plus 90 square plus 1. So this is 12 by 4, that is equal to 3. So 3 divided by 90 power 4 plus 90 square plus 1, that is the required torsion. Now for skew curvature, finally for skew curvature, we have this S square is equal to curvature square plus torsion square. So therefore there is nothing new that we have to evaluate for finding the skew curvature. Now let's take up some more exercises for practice purpose here. Find the curvature, torsion and skew curvature of the curve R of t is equal to a cos theta, a sin theta, a theta tan alpha. So in fact this is also a right circular helix, because the first two coordinates represent a circle and the third coordinate is a tan alpha into theta, and a into tan alpha is a constant and theta is a variable here. So this is also a right circular cylinder. That means, in other words, we are asking to find the curvature, torsion and skew curvature for a right circular helix. Now here we employ one more definition, that is radius of curvature, and similarly radius of torsion. By radius of curvature we mean like at a point where we have some given curvature of a curve, then using the same curvature, if we draw a circle, we will get a circle there. The radius of that circle can be called as the radius of curvature. And this if curvature is k, then the radius of curvature is denoted by rho, which is defined as 1 divided by curvature. And similarly the torsion, if torsion is denoted by tau, then the radius of torsion is denoted by sigma, which is equal to 1 divided by tau. So the reciprocal of curvature and torsion is actually the radius of curvature and the radius of torsion. Now let's take up one more exercise here. For the curve x equal to 3t, y equal to 3t square, z equal to 2t cube. Show that this radius of curvature is equal to minus times the radius of torsion, and this is equal to 3 divided by 2 into 1 plus 2t square whole square. Now we can clearly see that the curvature for this curve will be the reciprocal of this radius of curvature, and torsion will be the reciprocal of this radius of torsion. So here curvature is positive and the torsion is negative. And sometimes we can have the curves where they have the same curvature and the same torsion, and here in this case we have the curvature and the torsion are equal but opposite in sign. Find the radius of curvature and torsion for the curve x square plus y square equal to a square, x square minus y square is equal to az. Now here first of all, when we are given a curve as the intersection of two surfaces, we will always try to write down that curve in the parametric form. Here it is not so much difficult if we put x equal to a cos theta. So this first curve is the circle, which we know x is equal to a cos theta, and we can take y is equal to a sin theta. Then evaluate the difference x square minus y square, we will get z is equal to a cos 2 theta. So that will give us the parametric representation of the curve x equal to a cos theta, y equal to a sin theta. Then x square minus y square, that will be equal to a square cos 2 theta, but we already have one a here, so we will write z is equal to a cos 2 theta. So that's how we obtain the parametric representation of this curve also. Now let's take up some Formulas may directly be asked as a statement in examination. A necessary and sufficient condition for a curve to be a helix, is that its curvature and torsion are in constant ratio. We have already mentioned to find the curvature and torsion and skew curvature of right circular helix. For this thing we can mention down the answer here is curvature is equal to 1 by a cos square alpha, and torsion that is equal to 1 by a sin alpha and cos alpha. Now we can see that if we take the ratio of curvature and the torsion, we will get just the constant, some scalar, because a is a scalar here, a is a constant as well as alpha is a constant. So that means for this helix, we have the curvature and the torsion are in the constant ratio also. Therefore, we can say this is the necessary and sufficient condition for a curve to be a helix whenever their curvature and torsion are in constant ratio. So for any curve, whenever the curvature and the torsion are in constant ratio, that curve has to be a helix. Now let's take up one definition, that is a spherical curvature. Now this is like this sphere that has a 4-point contact with the curve at a point is called the osculating sphere, or this is also known as the sphere of curvature. Now a result regarding this sphere of curvature, the radius r of the sphere of curvature is given by r square is equal to rho square into sigma square into rho square. Now triple derivative of r whole square minus 1, where r of t equal to x of t, y of t, z of t is the given curve. So the parameters involved in finding the radius of sphere of curvature, it is rho square here, which is the radius of torsion. It is the radius of curvature, which we know it is equal to 1 divided by kappa, and sigma, which is the radius of torsion, this is equal to 1 divided by tau, and similarly again sigma square, rho square used here, which is the radius of curvature, and similarly r triple dot, so third derivative of the given curve whole square minus 1. In fact, we can use modulus here, minus 1. Then this is the radius of the sphere of curvature. Now we take another theorem which is also related to a curve and a sphere. So this is like this: a necessary and sufficient condition that a curve lies on a sphere is this rho divided by sigma plus derivative of sigma rho dash. This is equal to 0, where we have this rho, which is the radius of curvature. This is defined as the function of arc length s, and sigma is equal to sigma of s, which is again a radius of torsion. It is defined as the arc length of, it is defined as a function of arc length. And here in this derivative, we take the derivative of sigma into rho dash with respect to s. If this is equal to 0, then that is what it means by saying that the curve r of t lies on the sphere. And the sigma and rho, they are the radius of curvature as well as the radius of torsion for that curve. Now let's take up another definition, that is evolutes and involutes. We first define what we mean by evolute. The evolute of a regular curve, or we can say a regular plane curve, is the locus of the centers of curvature. In other words, we can say it is the path that is traced by the center of the osculating circle as we move along the original curve. Now it has the equation, let a plane curve be given by r of s. So here we deliberately use this curve is represented as the function of arc length, where s is the arc length. Then the evolute is, which we can denote by E of s, is equal to this r of s plus rho of s into neta, where this neta is also a n of s, and here this r of s is the given curve, rho of s is the radius of curvature, and n of s is the unit principal vector, or we can say a unit vector in the direction of the principal normal. Now similarly, we can define the involute. At each point, the involute lies along the tangent. Involute lies along a tangent to the original curve, and is orthogonal to the tangent at the point of contact. This is a better way to define an involute. Actually, an involute of a curve is constructed by unwrapping a taut string from the original curve. The end point of the string traces the involute as it unwinds. Now here we take up the parametric form for evaluating the equation of the involute. If we have the curve R is equal to R of S taken as a function of the arc length, then involute, which we shall call as I of S, is defined as R of S minus, now here we take the arc length, which we shall denote by L minus S, into the tangent, unit tangent vector T of S, where L is the arc length, total length of the curve, total length of the curve, and we are denoting this T, which is the unit tangent vector. So this is how we give the equation of involute to a given curve. Now here we mention certain properties. The first property being the evolute is the envelope of normals. Second, the curvature of the evolute is at a point is inversely proportional to the radius of curvature. And similarly, tangents to the involutes are normals to the evolutes. Tangents to involutes are normals to evolutes. And for this property is evolute of an involute, this gives the original curve. The evolute of a circle is a single point. The evolute of a circle is a single point, which is in fact the center of the circle. We can call this the center. So the center of a circle is the evolute of that circle. Now let's take up some properties of the parameters related with the curves. So these are properties of parameters related to the curves. First one is this first of all tangent. We have T double dash, T triple dash, that the scalar triple product of these three vectors. This is equal to, as by definition, this is equal to R double dash, R triple dash, R fourth derivative triple product of these three vectors. This is always equal to K cube, where K denotes the curvature, into K tau dash minus tau K dash, where kappa denotes the curvature of the curve and tau denotes the torsion of a curve, which can also be written as kappa power 5 into derivative of d by ds of kappa tau by kappa. So this is the property. Similarly, regarding the binormals, a similar property gives b dash, b double dash, b triple dash. Now each of this b is taken as a function of the arc length. This is equal to tau cube into kappa dash tau minus tau kappa dash, which is equal to tau power 5 into derivative of d by ds of k by tau. Similarly, we have like tau dash dot b dash is equal to minus k tau. Similarly, r dash dot r triple dash, this is equal to minus k square, and r dash dot r double dash, this is equal to 0, and r double dash dot r triple dash, this is equal to k into k dash, where k dash denotes the derivative of k with respect to s. Now we will take up one nice formula that we call the Serret-Frenet formulae. Now this is taken as a kind of a theorem. Serret-Frenet formulae. This is also a relation between the curvature, torsion and the normal, with the tangent to normal and the binormal. So the first part in the Serret-Frenet formulae is we define this tangent, that means t dash, which we can write as dt by ds. dt by ds, this is equal to kappa into n, where n is the unit normal vector. And similarly, second one, n dash is equal to dn by ds, where n is the principal normal vector or the unit principal normal vector, which is taken as a function of the arc length. This is equal to tau b minus kt, k tau. And similarly, the third one is b dash, which we can write as dB by ds. It is equal to minus tau n. Now here we mention one easy way to remember all these three. We just have to construct one determinant with the first row as 0, curvature, then again 0, then minus curvature, 0 tau, then 0 minus tau 0. Now multiply with this t and b, which are the unit vectors, tangent vector, normal vector, and the binormal vector, and equate them with their derivative t dash, n dash, and b dash. Now multiplying this matrix on the left hand side, this equation gives all the three Serret-Frenet formulae. Now we have some more properties related to these parameters associated with the curves. We have one new vector w is equal to tau into tangent plus curvature into binormal. So now here tau means the torsion, t means the tangent vector, k means the curvature, and b means the binormal vector. This is called the Darboux vector. Now once we have this Darboux vector, then this also gives us the three Serret-Frenet formulae. Then we have this t dash is equal to w cross t. So this is w taken its cross product with the tangent vector. This gives us the first Serret-Frenet formula for the t dash. Similarly, b dash, it is equal to w cross b. So w is also a vector. And similarly, n dash, this is equal to w cross n. So this is also the way as how we can define the three Serret-Frenet formulae using the Darboux vector. Now similarly, we have certain more properties. We mentioned certain more properties, they may not be the theorems. We have this tau is equal to 0, the torsion is 0 if and only if the curve is a plane curve. If and only if the curve is a plane curve. This is equivalently, or if and only if the scalar triple product, this r dash, or double dash, or triple dash is equal to 0. And similarly, we have this curvature is also equal to 0 if and only if the curve is a straight line. Now let's take up our one last topic related to the curves, and this is the Bertrand. So how do we define the Bertrand curves? This is two curves, C1 and C2 are said to be called the Bertrand curves, or we also called them as conjugate curves. If the principal normal to C1, is also a principal normal to C2. Now we take up certain properties of these Bertrand curves. The first one is the distance between the corresponding points. The distance between the corresponding points of two curves is constant. So the two curves are equidistant between any two corresponding points on them. Similarly, when they are equidistant with the distance being the constant, so the angles for tangents will also be the constant. So the angle between corresponding tangent lines is constant. So that's another property of the Bertrand curve. Third one, the torsion of two Bertrand curves is of the same sign. That means either the torsion is positive for both of them, or the torsion is negative for both of them, and their product is a constant. So the torsion for two Bertrand curves, so the product of the torsion of two Bertrand curves is constant. So these are certain properties of the Bertrand curves also. With this we conclude the topics related to the curves that may be asked in the entrance examinations. So thank you.